Hi everyone. So this is just a video on use of moles in questions in your exams. Going to just go through a little bit of like why we use moles as a concept and where it crops up, and then give you a few tips and tricks on how to answer questions on reacting masses, limiting reagents, and gas volumes and titrations. So just to start off, we're just going to look at this equation here and try and kind of explain to you where moles are kind of seen in this equation. So essentially the mole is just a number. It's a massive number, and it's a massive number because it represents a number of particles that is almost measurable in terms of the mass of them. There's no point counting molecules and atoms in groups of 1 or 10 or 100 because they'd weigh so little that it's very difficult to detect. So we use the mole as a concept in order to make our numbers relatable and usable, and just allows us to kind of manipulate the numbers a little bit easier. And so one of the things that you have to be able to do in order to use moles is to convert mass into moles and concentration and volume into moles, so that then you've got the format of moles to use the ratio to work out what reacts with what, and then you can convert back again. Now, in terms of this equation, where we see moles here are in the ratio of the atoms to each other in the molecules. This is a propane molecule, and you can see here, if I had 1 mole of propane molecules, what this formula tells me is that I have 3 moles of carbon atoms in that propane mole of propane molecules, and 8 moles of hydrogen atoms in a mole of propane molecules. Similarly, the big numbers in front of these molecules in this equation tell us how many moles of each of these react together and how many moles of each of these we make in relation to each other. So 1 mole of propane will react with 5 moles of oxygen to make 3 moles of carbon dioxide and 4 moles of water. Remember, mole is just a number, so I could equally have said 1 dozen propane molecules will react with 5 dozen oxygen molecules to make 3 dozen carbon dioxide molecules and 4 dozen water molecules. These are simply a ratio, and a mole is simply a number, just a number that we use to make our masses and concentrations a meaningful number that we can then manipulate when we do calculations. So with that in mind, let's have a look at a calculation and take you through the process. So here we've got that reaction again. We've got propane reacting with oxygen to make carbon dioxide and water, and we've got the ratio of what is made and what is used in there as well. So the first thing to recognize about converting masses into moles is that the mass of 1 mole of an atom, of an element, sorry, is in your periodic table. That's what the mass number is. So that tells you how many grams of that substance you need in order to have a mole of that element. And a mole just being this big number, 6 with 23 zeros on the end, a huge number. Now, in order to work out the relative, how much 1 mole of a compound weighs, we just add together how much a mole of each of the atoms are in there. So this substance here has 3 atoms of carbon and 8 atoms of hydrogen. So if I add together the relative masses of those things, so 3 carbons plus 8 hydrogens, I get 44. 2 lots of oxygens here for an oxygen molecule is 32. So 1 mole of propane weighs 44 grams. So if I have 88 grams of propane, then what I want to do first to work out how much oxygen is needed to react with that and how much carbon dioxide and water is made is I've got to convert that into a number of moles. And I do that by dividing 88 by 44. And that gives me 2 moles. So 88 grams of propane is 2 moles of propane. Now that will then react with a certain amount of oxygen. Now 1 mole of propane reacts with 5 moles of oxygen. So if I've got 2 moles of propane, that's going to react with 2 lots of 5 moles of oxygen, so 10 moles of oxygen. And that's going to make 2 lots of 3 moles of carbon dioxide, so 6 moles of carbon dioxide. And I'm going to make 2 lots of 4 moles of water, so 8 moles of water. So this ratio of 1 to 5 to 3 to 4 becomes, if I start with 2 moles of propane, 2 to 10 to 6 to 8. Okay. Now, in terms of what I can do next? Well, I can convert each of those moles into what that would weigh. So each mole of oxygen is going to weigh 32 grams for each of one of them. Each mole of carbon dioxide weighs 44 grams. Each mole of water weighs 18 grams. And then what I can do is convert that back into, okay, how much does 10 moles of oxygen weigh? How much does 6 moles of carbon dioxide weigh? So what this tells us is that 88 grams of propane reacts with 320 grams of oxygen to make 264 grams of carbon dioxide and also 144 grams of water. And I've converted there the moles into the mass of what that number of moles weighs. Okay. Now, in terms of using this ratio, I can now use the fact that I know how many moles of propane react with the amount of moles of oxygen, etc., to work out, well, what if I had different moles of each of these? So let's say, what if I only had 5 moles of oxygen? How many moles of ethane would react with that? And how much ethane would be left? So let's say I've got 2 moles of ethane, and I want to react that with 5 moles of oxygen. Well, what will react to that? 1 mole of the propane will react with the 5 moles of the oxygen, and 1 mole of the propane will be left over, because only 1 mole of propane reacts with those 5 moles of oxygen. What if I only had 3 moles of oxygen? Like this. Well, in that case, if I divide 3 by 5 to give me 0.6, that's how much propane will react. And so that's what happens. That amount of propane reacts with your oxygen, okay? And then from the 2 moles of propane I had, that amount of propane is left over. Now, this is the start of understanding how to work out limiting reactants, which we'll come to at the end of this video in terms of an example. Now, the 2 equations that you'll essentially be using throughout all of these reacting masses questions and titration questions, and indeed the gas volume questions, because you're given how much space a mole of gas takes up, we'll get to that in a second, are these 2 equations here. So if you can remember the triangles going into your exam, write them down as soon as you start the exam, and then you've got them right in front of you, and you've got the rearrangements as well, very easy to do. So the first one on this side is if you get given a mass of any substance in a reaction, you can always work out number of moles, because you can always work out the relative mass of that substance from looking up the elements in the periodic table. And then on this side, if you've been given a concentration of the volume, then you can work out the number of moles. One of the things just to make sure you do here is that your units are compatible. So your concentration will be in moles per dm cubed, and your volume is quite like to be given to in centimeters cubed. And again, we'll get to what we have to do there. To be honest, it's the same over here. Your mass and your relative mass needs to be compatible. Your mass needs to be in grams for your relative mass to be able to be used to work out moles. Okay, so let's look at some examples then, and I'll show you how I would then go about working these out using kind of a table method that you can use for any of these questions. So here's the first question I want us to look at. So it's a titration question that says the student titrated a solution containing 0.0045 moles of sodium hydroxide with 0.15 mole per dm cubed hydrochloric acid. And there's the equation, and you've got to calculate the volume. Now, I've been saying to you guys that you should always just think about how can I work out moles first. You're always going to get marks for working out number of moles, but in this question, you've been given number of moles, and so you go to the next step in the process, which is using the ratio to work out the moles of the other thing that you're trying to work out. Now, we're trying to work out the volume of hydrochloric acid, so eventually we need the moles of hydrochloric acid in order to work out the volume. Now, I would use a table to do this, so if I show you that. So here's my table, and you can see I've set it out with the substances and concentration, volume, moles, and ratio. The reason why I put concentration and volume here is because I'm working out a volume, and I've been given a concentration. So this is not mass, relative mass to work out moles, it's concentration and volume that I need. Now, in the question, I've been given information about sodium hydroxide and hydrochloric acid, and I'm working out the volume of hydrochloric acid. Now, these are both the reactants. And so whilst I've written out this whole table, I don't actually need this side of the table at all. So I can just strike out those two substances. I'm not even looking at those. So in terms of how to work this out, first, what have I been given? Well, I've been given the number of moles of sodium hydroxide, and I've been given the concentration of hydrochloric acid. So I can put, and I'm trying to work out the volume of hydrochloric acid. So I've been given number of moles sodium hydroxide, and so that is 0.0045, and I've been given the concentration of hydrochloric acid, 0.15. I'm trying to work out the volume. Now, the first thing I should do after this, after I've got the number of moles, is to go to the ratio. And my ratio is 1 sodium hydroxide to 1 hydrochloric acid. I get my ratio from the chemical equation. And then I can work out my moles of hydrochloric acid, because if it's 1 to 1, then the number of moles of hydrochloric acid that will react to sodium hydroxide is the same as the number of moles of sodium hydroxide. So there's my moles of hydrochloric acid the same, because it's a 1 to 1 reaction. If this was 2 to 2, it would be the same as well. 3 to 3, it'll be the same as well. So in terms of my next step, well, I'm trying to work out my the volume of hydrochloric acid. I'm trying to work out this. And so what I'll do to work that out is to use the triangle that has concentration and volume in. Now, moles equals concentration times volume. So my volume is going to be my moles divided by my concentration. So 0.0045 divided by 0.15, and that gives me 0.03 decimeters cubed. Now, if we go back to the question, actually, it wanted it in centimeters cubed. So to convert decimeters cubed into centimeters cubed, then I need to type. Okay, so let's look at this question now. So it's a bit more in depth because we haven't been given a number of moles. So it says titanium is extracted from titanium dioxide in a two-stage process. Here's the equation, and I've got to calculate the volume of chlorine gas needed to react completely with 100 kilograms of titanium dioxide, being given some relative masses, and I've got 1 mole of gas takes up 24 decimeters cubed of space. You never have to remember that number. It'll always be given to you. So let's look at how we answer this question. So let's have a little look at this question together then. So let's highlight the numbers first. And you could have a go at this question first. Pause it now if you wish. But I'll go through it now. So you've got 100 kilograms of titanium dioxide. You've got the fact that you've got the relative masses here. You've got the fact we're calculating the volume of chlorine gas. So the first thing to do is to get this mass of titanium dioxide into my table. Now I've got kilograms here, and I've got to convert that into grams. So I'm going to time this by 1,000. That gives me 100,000 as my grams of titanium dioxide. My relative mass of titanium dioxide I can work out by adding together 1 lot of titanium with 2 lots of oxygen. If I do that, I get 80. And so my moles is going to be the mass divided by my relative mass, which gives me 1,250 moles of this titanium dioxide. So I've got my moles. My next step is my ratio. Now, a ratio I get from my equation. So my ratio is 1 to 2. So 1 mole of titanium dioxide reacts with 2 moles of chlorine. So if I've actually got 1,250 moles of titanium dioxide, I've got to multiply that by 2 to get my moles of chlorine, which is 2,500. Now I don't need this area now, because actually what I'm trying to work out is the volume of gas that is created. And I know that 1 mole of gas takes up 24 decimeters cubed of space. So all I've got to do is multiply this number of moles of the chlorine by 24, and that gives me my answer, which is 60,000 decimeters cubed. Okay, so next one is this again. So you could pause it now to try it, or you could just carry on watching. And so let's have a look at this in a bit more detail. So let's highlight the numbers we have. We have a mass of silicon dioxide. We have some relative masses, and we're trying to calculate the minimum mass of magnesium that needs to, it says to completely reduce this, it means react with it, okay, so we've been given a reaction. So we're not looking again at anything to do with the silicon, or the magnesium oxide, we're just looking at this side. And that's not always going to be the case. Sometimes you'll be asked how much of this can be made, but in this case, we're looking again at the reactants. So let's put into our table what we've got. Well, we've got a mass of silicon dioxide. Again, it's in kilograms, so I've got to convert it into grams by timesing by 1,000. And from that, I can work out number of moles because I can work out the relative mass of silicon dioxide. It's going to be 28 plus 2 lots of 16, which gives me 60. I can also work out my relative mass of magnesium, and I may as well put that into my table. It is just 24. So in terms of working out moles, well, I'm going to do mass divided by relative mass, which gives me 20. And then I need my ratio to work out number of moles of the magnesium that reacts with the silicon dioxide. My ratio is 1 to 2. So 1 mole of silicon dioxide reacts with 2 moles of magnesium. So if I've got 20 moles of silicon dioxide, well, that's going to make, or need, sorry, 40 moles of magnesium in order to react with it. So to work out my mass of magnesium, I look back at my triangle, which you should have in front of you when you've written it down when you start the exam. 40 multiplied by 24, and that gives me 960 grams. Okay, again, you could pause this now, try the method. Remember, you're working out moles, then use your ratio, then use the relevant triangle. So if we go through this one then, we've got calculate the concentration of hydrochloric acid, so that's this one, and we've been given information about barium hydroxide, which is this one. So again, actually, we're not talking about this one, and we're not talking about this one at all in this question. So in terms of what we've been given a volume of hydrochloric acid, we've been given a volume and the concentration of the barium hydroxide, and we've been asked to calculate the concentration of the hydrochloric acid. So let's fill in our numbers. We've been given the fact we've got 25 centimeters cubed of the hydrochloric acid, which isn't the unit we need because the concentration is in moles per decimeter cubed. So to convert centimeters cubed into decimeter cubed, we divide by 1,000. So there we are, it's 0.025. And again, we've been given a volume of the barium hydroxide, divide by 1,000, and that gives us 0.0235 decimeters cubed. Now, in terms of the concentration, well, the concentration being given is barium hydroxide, 0.1. And so to work out moles, I multiply these together, and that gives me 0.00235 moles of barium hydroxide. So now I've got my moles, I then need to use my ratio, which is 1 to 2 again. So 1 mole of this reacts with 2 moles of this. So if I've got 0.00235 moles of this, I'm going to multiply by 2 to get my moles of the hydrochloric acid that reacts with it. And then to work out my missing concentration, well, I need the relevant triangle. And the relevant triangle here is the concentration volume moles one. Moles equals concentration times volume. So my concentration equals moles divided by volume. And if I do that, I get 0.188. Okay, this is the final question I'm going to go through, which is a reacting masses question. I want to show you that you can still use this kind of table method to answer these questions as well. So let me show you how to do that. You can pause it now to try this. So again, let's highlight what we've got and what we're trying to do. So we've been given the fact we've got 1 kilogram of aluminium and 3 kilograms of iron oxide. They're these two substances here. So those are two amounts we're trying to react together, but they will not react together perfectly. There'll be some of one of them left over because we've got more than enough of one of them, and not all of it reacts. Now it's asking us to show that the aluminium is the limiting reactant. Okay, so actually we're showing we've got iron oxide left over if we react this amount of these together. So we can do that using this process again. So first step, again, work out number of moles of each of those that you have. So for aluminium, if I've got, first I want to work out the mass. I've got 1,000 grams of aluminium because it's 1 kilogram, and I've got 3,000 grams of iron oxide because it's 3 kilograms. I can work out the relative masses. So I've got the relative mass of aluminium is 27. My relative mass of iron oxide, if I add it all up, is 160. Now with these two numbers and these numbers, I can work out number of moles of each that I've got to start with. But actually what I want to do here is work out the moles of the aluminium that I've got, and then work out how many moles that I need of the iron oxide, with that, and then show that I've got more iron oxide than actually that I need to react to this amount of aluminium. So I'm going to work out moles of aluminium, which is 37.04, 1,000 divided by 27, and I use my ratio of 2 to 1 from the equation to work out how many moles of iron oxide wouldn't be needed to react this number of moles of aluminium, and that is 18.52. Now, if I use this number of moles and this relative mass to work out how much iron oxide I actually need to react with the aluminium, if I multiply those together, then actually what I get is 2,963.2 grams. And you can see that is less than the 3,000 that I've actually started with. And that's the whole point here. I'm showing that's the case. So that's the sentence I could put at the end, obviously with subscripts and not big numbers there, apologies, a bit of a typo there. But this is less, this number that I've worked out that I need to react to this 1,000 grams of aluminium, that's less than the iron oxide that's available. So that means there's going to be some of this iron oxide left over, and that means the aluminium is going to run out first, which means it's limiting. Okay, so hopefully that's helped a little bit. What I would suggest is you use a table like this if you remember how to lay it out, and we'll do some practice in lesson as well. But the process is pretty much always work out number of moles, use the ratio to work out moles of the other thing, and then use the appropriate triangle to work out the quantity that you've been asked to work out in the question. And if you do that, then you're going to get at least some of these marks that are available. You might forget a conversion or something like that, but you're going to get some of these marks that are available. And that's the whole idea as you go through this paper, picking up marks where you can. Okay, I'll leave that there. If you want to have any questions, then don't hesitate to email me or ask me in class.